Right now, as you read these words, the most powerful radio telescopes ever built by human hands are listening. They are pointed at the sky, scanning frequencies across the electromagnetic spectrum, sifting through the static of the cosmos, with instruments so sensitive they could detect the equivalent of a mobile phone signal from the distance of Jupiter. They have been listening for decades, thousands of hours of observation time, millions of dollars of engineering, generations of scientists who dedicated their careers to a single question. And what they have heard across all those years, across all those frequencies, across a sky containing more stars than there are grains of sand on every beach on Earth, is silence. Not the silence of a room at night, where you can still hear your own breathing, your own heartbeat, the distant murmur of a world that is alive. A different kind of silence. The silence of a frequency that carries nothing. The silence of a signal that was never sent or was sent and vanished, or was sent, and we do not yet have the instruments to hear it. The silence of a universe that by every calculation we can perform should be teeming with voices, and yet returns to us nothing but the cold hiss of background radiation left over from the first moments of creation. This silence has a name. Scientists call it the Fermi Paradox, but paradox is too gentle a word for what it actually represents. A paradox is an intellectual puzzle, a curiosity, something that makes you furrow your brow and reach for a pencil. What the silence of the universe actually represents is something closer to a verdict, a judgment handed down by the cosmos itself about the nature of intelligence, the rarity of consciousness, and the fate of civilizations. And depending on which explanation turns out to be correct, that verdict is either the most humbling and beautiful thing the human mind has ever confronted, or the most terrifying. If you find yourself drawn to questions that do not have comfortable answers that pull you to the edge of what human understanding can reach and invite you to look over, do me a small favor and hit that like button and subscribe. It genuinely helps this channel continue making journeys like this one. Now, get yourself comfortable and keep the lights on if you prefer. Let's begin. To understand why the silence is so strange, you first have to understand what the universe looks like from a statistical standpoint. Not from the ground looking up at a sky that seems vast, but manageable, a dome of stars that a human eye can survey in a single night, from above, from outside, from the perspective of a mind trying to hold the full architecture of the cosmos in a single thought. The Milky Way, our galaxy, the structure of stars and gas and dark matter that contains our sun, our solar system, and every human being who has ever lived, contains an estimated 200 to 400 billion stars. That number is so large that it resists intuition entirely. 400 billion. If you tried to count them at a rate of 1 per second without sleeping, without stopping, if you tried to count them at a rate, it would take you roughly 12700 years to finish. You would have started counting before the first city was built, before the first written language existed, before the wheel was invented, and you would still be counting now. And the Milky Way is one galaxy, one structure among approximately 2 trillion galaxies in the observable universe. 2 trillion galaxies, each containing hundreds of billions of stars. The total number of stars in the observable universe is estimated at approximately 10 to the power of 24. That is a 1 followed by 24 zeros. It is a number so far beyond human comprehension that even describing it as incomprehensible fails to capture the depth of the incomprehension. There are more stars in the observable universe than there are atoms in a grain of sand. More stars than there are grains of sand on every beach, and desert on Earth combined multiplied by a factor that itself defies description. Now, consider what we know about those stars. NASA's Kepler Space Telescope, launched in 2009 and operational until 2018, surveyed a small patch of sky containing roughly 1500000 stars and found planets around the majority of them, not a few. Not a surprising fraction, the majority. Statistical analysis of the Kepler data suggests that virtually every star in the Milky Way hosts at least one planet. Some host many. Our galaxy alone contains an estimated 1 trillion planets, perhaps more. Of those planets, a significant fraction orbit their stars within the habitable zone, the range of distances where liquid water can exist on a planetary surface. Liquid water is, as far as we understand, a prerequisite for life as we know it. Some estimates place the number of potentially habitable planets in the Milky Way alone at several billion. Several billion worlds in our galaxy circling at the right distance from the right kind of star, with the right conditions for the chemistry that produces living things. And the Milky Way is 13.6 billion years old. Life appeared on Earth within roughly a billion years of the planet's formation. If similar timelines apply elsewhere, and there is no obvious reason they should not, then the galaxy has had billions of years in which life could have emerged, evolved, developed intelligence, built technology, and reached out across the void. By every statistical measure available to us, the universe should be full of life, not just microbial life, not just simple organisms clinging to the rocks of some distant world, but complex life, intelligent life. Civilizations that have had millions or billions of years longer than we have to develop their science, their technology, their means of communication and travel. Civilizations so advanced relative to us that the comparison makes our most sophisticated technology look like a child's drawing of a rocket ship. And yet, silence. This is the Fermi Paradox, and it was born not in a laboratory or at a conference or in the pages of a scientific journal. It was born at a lunch table in Los Alamos, New Mexico in the summer of 1950 inches, the mind of a man who had already helped reshape the world once and was not yet finished thinking about it. Enrico Fermi was, by any measure, one of the most extraordinary scientific minds of the 20th century. Born in Rome in 1901, he had demonstrated a capacity for physics so extraordinary that his professors ran out of things to teach him before he finished university. He won the Nobel Prize in Physics in 1938 for his work on nuclear reactions induced by neutron bombardment. He played a central role in the Manhattan Project, overseeing the construction of Chicago Pile, the world's first artificial nuclear reactor, which achieved its first self-sustaining chain reaction on December 2nd, 1942 inches to a converted squash court beneath the stands of a football stadium at the University of Chicago. The man understood nuclear physics at a level that few human beings have ever matched. But Fermi was also famous among his colleagues for a different kind of thinking. He was a master of what physicists call Fermi estimation, the ability to arrive at surprisingly accurate answers to seemingly impossible questions using only basic reasoning and rough approximations. How many piano tuners are there in Chicago? How many golf balls fit in a school bus? How many atoms are in a human body? Fermi could work through these problems in minutes, sketching calculations on a napkin, and arrive at answers within an order of magnitude of the truth. It was a habit of mind that cut through complexity to reveal the underlying structure of a problem. So, when Fermi sat down to lunch with his colleagues at Los Alamos that summer day in 1950, and the conversation turned to a recent cartoon in The New Yorker depicting flying saucers stealing garbage cans from New York City, it was perhaps inevitable that his mind would drift toward numbers. He began almost casually to sketch through the mathematics of extraterrestrial civilizations, the age of the galaxy, the number of stars, the fraction that might host planets, the fraction of those planets that might develop life, the fraction of those that might develop intelligence, the timescales involved. And at the end of this chain of reasoning, Fermi looked up from his mental calculations and asked a question so simple, so devastating, so perfectly targeted at the heart of the problem that it has echoed through the scientific community for more than 70 years. Where is everybody? Not as a dramatic proclamation, not as a rhetorical flourish, as a genuine question spoken across a lunch table in the tone of a man who had just noticed that the numbers did not add up. The universe is old. The galaxy is full of stars. The stars have planets. The timescales involved are enormous. If even a tiny fraction of those planets developed civilizations capable of space travel or electromagnetic communication, there should be evidence of them everywhere. The sky should be buzzing with signals. The galaxy should bear the fingerprints of engineering on cosmic scales. We should have heard something by now, but we have not. Where is everybody? The question sat at the table like an uninvited guest, and it has never left. In the decades since Fermi asked it, it has grown from an offhand lunchtime observation into one of the central unsolved problems in science. Physicists, astronomers, astrobiologists, philosophers, and mathematicians have all taken their turn at it. They have proposed dozens of explanations, some mundane, some disturbing, some so profound in their implications that they alter the meaning of human existence itself. And none of them have been proven correct. None of them have silenced the question. None of them have fully explained why, in a universe of this age and this scale, we have heard nothing, not a signal, not a pattern, not a whisper. The silence continues, and the longer it continues, the more weight it accumulates, because silence in statistics is data. The absence of a signal is itself a signal. When you listen for something across a sufficient range of frequencies and distances and times, and you hear nothing, that nothing is telling you something. The universe is sending us a message in the only medium it has chosen to use with us so far. And that message is the absence of any message at all. Before we examine what that silence might mean, we need to understand how strange it truly is. Not in the abstract, not as a philosophical puzzle, but as a concrete physical strangeness. The kind of strangeness that becomes apparent when you sit with the numbers long enough for them to stop being numbers and start being reality. Consider the age of the universe, approximately 13.8 billion years. The Milky Way formed roughly 13.6 billion years ago. Our solar system formed about 4.6 billion years ago. That means the galaxy was already more than 9 billion years old before our sun ignited. 9 billion years. In that time, stars were born and died and scattered their heavy elements across the galaxy. Elements like carbon, oxygen, nitrogen, iron, the building blocks of chemistry, of biology, of everything a living thing requires. Those elements were available in the galaxy long before Earth existed. If life tends to emerge within 1 billion years of a planet's formation as it did on Earth, then civilizations could have been arising and developing in the Milky Way for 8 or 9 billion years before humanity took its first steps. If even one of those civilizations developed space travel and began expanding through the galaxy at even a fraction of the speed of light, 1%, 1/10%, they could have reached every star system in the Milky Way within a few 100 million years. 100 million years sounds enormous to human ears, but it is less than 1% of the galaxy's age. It is a geological eye blink. It is nothing. A civilization that began expanding through the galaxy 9 billion years ago at 1% of the speed of light would have reached Earth 7 or 8 billion years before the first life appeared here. They would have had billions of years to colonize this solar system, to alter this planet, to leave behind artifacts or signals or structures that we would be finding in our rocks and our sky today. And we have found nothing. No artifacts, no structures, no signals, no evidence of any kind that anyone has ever been here or anywhere nearby before us. This is what makes the silence strange. Not merely that we have not heard from anyone, but that in a galaxy old enough and large enough that a single expanding civilization could have filled it billions of years ago, there is no sign that this has happened. The galaxy looks for all our instruments can determine as if we are the first ones to look up and wonder. And that should not be possible. The math says it should not be possible. The age of the universe says it should not be possible. And yet here we are in the silence with our radio telescopes pointed at the sky and our equations telling us the sky should be full and reality, returning to us nothing but static and the cold background hum of creation. There is a word for the distance between what the equations predict and what the universe delivers. Scientists sometimes call it the Great Silence. A silence so complete, so total, so perfectly undisturbed across every frequency we have searched and every direction we have looked that it has begun to feel less like an absence of evidence and more like evidence of absence, less like a puzzle waiting to be solved and more like an answer we have not yet learned how to read. The question is what that answer says, and every possible reading of it changes something fundamental about how we understand our place in the cosmos. Because here is what we know with certainty. The universe is vast beyond imagining. It is ancient beyond reckoning. It has had more than enough time and more than enough raw material to produce intelligence 1,000 times over, 1,000,000 times over, in every corner of every galaxy that exists. And yet we sit here in our small corner of one ordinary galaxy, surrounded by a silence so profound that it has become the loudest thing in the universe. That silence is the beginning of this story, but it is not the end, because silence, unlike sound, does not simply exist. It has to be explained, and the explanations, every single one of them, lead somewhere extraordinary. The story of the Fermi Paradox might have remained a lunchtime curiosity, a clever observation spoken across a table and forgotten with the afternoon, had it not been for a young astronomer in West Virginia who 11 years after Fermi's question decided to do something no one had seriously attempted before. He decided to listen. Frank Drake was 30 years old in the spring of 1960. He had a radio telescope at the National Radio Astronomy Observatory in Green Bank, West Virginia, a quiet valley chosen precisely because its surrounding mountains shielded it from the electromagnetic noise of human civilization. He had a frequency in mind, 1420 megahertz, the emission frequency of neutral hydrogen, the most abundant element in the universe. The reasoning was elegant. Any civilization advanced enough to build a radio telescope would know about hydrogen. Any civilization that wanted to be heard would broadcast near a frequency that other radio astronomers would naturally be monitoring. It was, Drake believed, the cosmic equivalent of a lighthouse frequency, a channel that intelligence would choose because intelligence would recognize it. He called his project Ozma, after the queen of the fictional land of Oz, a place very far away and difficult to reach. He pointed his telescope at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, each within about 12 light-years of Earth. He listened for 6 hours a day over the course of several months. His equipment was by modern standards almost comically primitive. A single receiver, a single frequency, a single antenna, an output recorder that printed signal strength on a paper strip like an old seismograph. He heard nothing useful. A brief burst of signal early in the program turned out to be a classified military aircraft. After that silence. But Drake was not discouraged. He was, if anything, energized, because, in the process of designing Project Ozma, he had done something that would prove far more consequential than the project itself. He had written an equation. In November of 1961, Drake organized the first scientific conference ever held on the subject of extraterrestrial intelligence. It took place at Green Bank in a small conference room attended by fewer than a dozen scientists, including a young Carl Sagan and a dolphin researcher named John Lilly, who had been invited because dolphins represented, at least in theory, a non-human form of intelligence. Drake wanted to organize the discussion, to give the participants a framework for thinking about the problem systematically. So he wrote on the blackboard a string of variables multiplied together, and told the room that the product of these variables would give them an estimate of the number of communicating civilizations in the Milky Way right now. The Drake equation, as it came to be known, is not a physical law. It does not describe a measurable quantity in the way that Einstein's field equations describe space-time or Maxwell's equations describe electromagnetism. It is a framework, a way of organizing ignorance, a method of laying out in mathematical form all the things we do not know about the emergence of intelligence in the universe, so that as we learn more we can plug in better numbers and refine the estimate. The equation has 7 terms: the rate at which new stars form in the galaxy each year, the fraction of those stars that have planets, the average number of planets per star that could support life, the fraction of those planets where life actually emerges, the fraction of those where life develops intelligence, the fraction of intelligent civilizations that develop detectable technology, and finally, the length of time such civilizations remain detectable, either because they survive and keep broadcasting, or because they collapse and go silent. Multiply all 7 terms together, and you get n, the estimated number of technologically communicating civilizations in the Milky Way at this moment. When Drake and his colleagues worked through the equation in 1961, their estimates were necessarily rough. They knew almost nothing about the frequency of planets around other stars. They knew nothing about the conditions that favor life. They were guessing at several of the terms with very little data to anchor the guesses. Their estimates of n ranged from a handful to millions, a range so wide it was essentially a confession of ignorance dressed up in the language of mathematics. But the equation did something more important than produce a number. It revealed the structure of the problem It showed that the question of extraterrestrial intelligence was not one question but 7, and that answering any one of them would sharpen the estimate dramatically. It gave the scientific community a map of what they needed to learn, and it established clearly and permanently that the question of whether we are alone in the universe was not a matter of philosophy or religion or speculation. It was a matter of science, a question with a quantitative answer that could in principle be calculated once the relevant data was gathered. In the 6 decades since Drake wrote his equation on that blackboard, the data has improved enormously for some of the terms and remained stubbornly elusive for others. The first 2 terms, the rate of star formation and the fraction of stars with planets, are now known with reasonable precision. Astronomers have measured the star formation rate of the Milky Way at roughly 1 to 3 new stars per year. The fraction of stars with planets, thanks primarily to the Kepler mission and its successor TESS, the Transiting Exoplanet Survey satellite, is now understood to be close to 1. Nearly every star has planets. Not every star has Earth-like planets in habitable zones, but the fraction that do is substantial. Estimates range from a few percent to more than 20% depending on the assumptions used. Let us work through the arithmetic carefully, because the numbers are where the strangeness lives. If the Milky Way contains 300 billion stars and roughly 20% of them host planets in habitable zones, that gives us 60 billion potentially habitable worlds in our galaxy alone. 60 billion. If even 1% of those worlds developed life of any kind, that is 600 million worlds with biology. 600 million planets in this galaxy, where chemistry organized itself into self-replicating structures, where cells emerged and divided and evolved. If even 1% of those went on to develop complex multicellular life, that is 6 million worlds with animals, with ecosystems, with the kind of biological complexity that on Earth eventually produced nervous systems and brains. And if even 1% of those produced intelligence, that is 60,000 civilizations in the Milky Way alone that develop minds capable of asking questions about the universe they inhabit, 60,000 civilizations in one galaxy, from assumptions that are, if anything, conservative. Now let us make the assumptions more conservative still. Let us say that the fraction of habitable planets that develop life is not 1%, but 1 in a million. Let us say the fraction that develops intelligence is not 1%, but 1 in a million of that. We are now dealing with probabilities so small they strain credulity, and still given 300 billion stars and the timescales involved, the expected number of intelligent civilizations to have ever arisen in the Milky Way remains comfortably above 1, above us. This is what makes the silence so statistically violent. You can make the assumptions increasingly restrictive, can pile pessimism upon pessimism, can assume that life is extraordinarily rare and intelligence is rarer still, and the math keeps returning a number larger than 1. The universe is so large and so old that even vanishingly small probabilities multiply out to produce expected values that should have left some trace, some signal, some mark on the cosmos that our instruments could detect. To make this visceral, consider a scale model, not of distance this time, but of time. Compress the entire history of the Milky Way 13.6 billion years into a single calendar year. Each month represents roughly 1.1 billion years. Each day represents about 37 million years. Each hour represents about 1.5 million years. Each minute represents about 2,600,000 years. On this calendar, the Milky Way forms on January 1st. The first stars ignite within the first few days. By February, the galaxy already contains heavy elements from dying stars, the raw material of chemistry and biology. The oldest stars capable of hosting Earth-like planets around them begin forming before the end of January. If life tends to emerge within a billion years of planetary formation, then the first potential biospheres in the galaxy could have appeared as early as February or March on our calendar. That is 10 or 11 months before Earth even exists. Our solar system does not form until early September. Earth's surface cools and liquid water appears around mid-September. The first microbial life on Earth appears around late September. Complex multicellular life does not emerge until mid-November. Dinosaurs appear in early December and are gone by December 25th. Modern humans, Homo sapiens, appear in the last 2 hours of December 31st. All of recorded human history, every civilization, every war, every scientific discovery, every work of art, every word ever written occupies the last minute and a half of December 31st. Now, consider a civilization that arose not in September, not in November, not in December, but in March. A civilization that had its equivalent of our last minute and a half of December, not at the end of the year, but 9 months earlier. A civilization with 9 months of additional development. At the rate that human technology has progressed in the last 200 years, 9 months on this calendar represents roughly 9 billion years of additional development time. What does a civilization look like after 9 billion years of technological progress? We cannot know. We have no reference point. We have existed as a technological species for perhaps 200 years, a span so short on the cosmic calendar that it does not even register as a pixel. To ask what a 9 billion-year-old civilization looks like is to ask a bacterium to describe the internet. The question exceeds the capacity of the mind being asked to answer it. But here is what we can say. A civilization that old would not be hiding. It would not be limited by the speed of chemical rockets or the range of radio waves. It would have had time many times over to spread through the galaxy by whatever means physics permits, to build structures on scales that would be visible from thousands of light years away, to alter the energy output of stars, a concept called a Dyson sphere, a structure built to capture the total energy of a star, first proposed by physicist Freeman Dyson in 1960, to communicate using methods so powerful and so omnidirectional that a civilization at our level of development would inevitably detect them, even accidentally, even without trying. We have detected none of this. Not a Dyson sphere, not a megastructure, not a signal on any frequency, not an artifact in our solar system, not a pattern in any dataset, not a whisper. And this brings us to the most uncomfortable aspect of the Drake equation, the terms we cannot measure, the fraction of planets where life emerges, the fraction where intelligence develops, the fraction where intelligence survives long enough to be detectable. These terms remain almost entirely unknown. We have exactly one data point for the emergence of life Earth. We have exactly one data point for the emergence of intelligence Earth. We have exactly one data point for the longevity of a technological civilization, Earth. And we have existed as a technological civilization for such a short time that our own data point is essentially useless for estimating longevity. One data point for a universe of 2 trillion galaxies and 10 to the power of 24 stars. Imagine trying to determine the average height of all human beings on Earth by measuring a single person. That is the quality of data we are working with when we try to estimate the prevalence of intelligence in the cosmos. We have looked at one example ourselves, and we are attempting to extrapolate to a population of trillions. Carl Sagan, who spent much of his career thinking about the Fermi Paradox, was an optimist about the prevalence of life in the universe. He believed the galaxy was likely full of civilizations, and that the silence was a problem of distance and time rather than a problem of rarity. He argued that with a galaxy 1,000,000 light-years across, and communication signals traveling at the speed of light, civilizations might simply be too far apart, their signals too diluted by distance, their technological windows too narrow for contact to have occurred yet. He estimated using optimistic values for the Drake equation that the number of communicating civilizations in the Milky Way right now could be in the millions. Millions. 1 million civilizations in this galaxy alone, each broadcasting, each listening, each waiting for contact, and none of them hearing each other because the galaxy is simply too large and the signals too faint. To feel the force of this argument, consider what happens to a radio signal as it travels through space. Radio waves, like all electromagnetic radiation, spread outward from their source in a sphere. As the sphere expands, the energy is distributed over an ever larger surface area. The signal weakens in proportion to the square of the distance. Double the distance, and the signal strength drops to 1/4. Triple it, and it drops to 1/9. At interstellar distances, even the most powerful radio transmissions ever generated by human technology would be essentially undetectable by the time they reached the nearest star system. The most powerful, deliberate radio transmission humanity has ever aimed at the stars was the Arecibo message broadcast 25000 light-years away. The message was 1679 binary digits long, encoding information about mathematics, the structure of DNA, the human form, and the location of Earth in the solar system. It was broadcast at a frequency and power level calculated to be detectable by a radio telescope similar to Arecibo at the receiving end. The message is still traveling. It has covered roughly 50 light-years in the 50 years since it was sent, approximately 1/5 of 1% of the distance to its intended destination. It will not arrive for another 24950 years. And if no one at M13 is pointing a telescope at exactly the right frequency at exactly the right moment when the signal arrives, compressed by distance to a whisper, indistinguishable from the background noise of the cosmos, they will not hear it at all. This is the galaxy at the scale that matters for communication, 100,000 light-years across, signals traveling at the speed of light, weakening with every light-year of travel, arriving at their destinations tens of thousands of years after they were sent. Two civilizations separated by 5,000,000 light-years and broadcasting simultaneously might not exchange a single meaningful message in the entire lifespan of either one. Perhaps the silence is simply this: we are shouting into a room the size of a continent and expecting to be heard from across it with equipment designed for a living room. Perhaps the galaxy is full of voices, each one isolated by the sheer physical scale of the structure they inhabit, each one broadcasting into a darkness so vast that their signals fade to nothing before reaching anyone who might listen. This is the optimistic interpretation, and it is genuinely comforting. It suggests that the universe is full of life, full of intelligence, full of civilizations just like ours, or vastly beyond ours, each one separated from the others, not by extinction or silence, but by distance and time, each one broadcasting, listening, waiting in a galaxy so large that the light from their transmitters will take longer to reach us than our entire civilization has existed. But comfort in the Fermi Paradox has a habit of being temporary, because for every optimistic explanation of the silence, there is a darker one that fits the same data. And the darker explanations do not merely suggest that we have not heard anyone yet. They suggest something about the nature of intelligence itself, about the trajectory of civilizations, about the future that awaits any species advanced enough to ask the question in the first place. The optimistic explanation says, the silence is a problem of scale. We simply have not listened long enough or loudly enough, or at the right frequencies or in the right directions. The universe is too large for contact to have occurred yet, and our technology is too primitive to detect the signals that might be out there. But there is another explanation, one that does not require the universe to be too large or our instruments to be too primitive, one that fits the silence not as a consequence of distance, but as a consequence of something that happens to every civilization that reaches a certain level of development, something that explains not merely why we have not heard anyone, but why the galaxy looks in every direction we examine it as though no one has ever been here. That explanation is the great filter, and it changes everything. But before we get there, we need to spend time with the scientists who have dedicated their lives to breaking the silence, because the history of the search for extraterrestrial intelligence is not merely a history of null results. It is a history of extraordinary moments of signals that flickered at the edge of detection and then vanished, of data that looked for a breathtaking instant like exactly what we were hoping to find. And the story of those moments, of the hope they contained, and the silence that followed, tells us something that no equation can capture about what it means to listen for a voice in the dark and hear nothing in return. There is a particular kind of dread that comes not from what you know, but from what the absence of knowledge implies. When a child does not come home at the expected hour, the fear that settles in the parent's chest is not caused by evidence of harm. It is caused by silence, by the gap between what should have happened and what has. The Fermi Paradox operates on exactly this principle, scaled to the size of the universe. The silence is not evidence of nothing. It is evidence of something, and the question that has occupied some of the finest scientific minds of the last 70 years is what precisely that something is. The explanations fall into broad categories. Some are benign, some are unsettling. Some, if true, would constitute the most terrifying fact ever discovered about the universe we inhabit. And the most disturbing aspect of all of them is that no one can yet determine which one is correct. We are sitting in the silence, surrounded by explanations, and every single one of them changes the meaning of human existence in a different and profound way. The first category of explanation is the one scientists sometimes call the zoo hypothesis, or more broadly, the non-interference family of solutions. The idea is simple. They are out there. They know we are here, and they have chosen not to contact us. Perhaps for ethical reasons, perhaps because they are observing us as we observe animals in their natural habitats. Perhaps because they have determined that premature contact would be damaging to a developing civilization. Perhaps there is a galactic protocol, a set of conventions agreed upon by advanced civilizations that forbids interference with species that have not yet reached a certain threshold of development. We are on this view, a protected species living in a cosmic nature reserve, observed but not approached, studied but not contacted, watched with the patient attention of researchers who understand that the most valuable data comes from civilizations that develop in isolation. This explanation has an obvious emotional appeal. It places us in a universe that is full of intelligence, that is aware of us, that has chosen to leave us alone out of respect or caution or scientific protocol. It is in a sense the most flattering possible interpretation of the silence. We are not alone. We are simply being given space to grow. But the zoo hypothesis has a fundamental structural weakness that most scientists find fatal. It requires that every advanced civilization in the galaxy, every single one, over billions of years agrees to and maintains this policy of non-interference without exception. Not most of them, all of them, because all it would take is one civilization out of potentially millions to break the protocol, one curious explorer, one rogue faction, one civilization that disagrees with the consensus and decides to make contact anyway. The history of human civilization is a history of individuals and groups that refuse to follow the rules that everyone else agreed to. The idea that an advanced civilization, let alone every advanced civilization simultaneously, could maintain a perfect embargo on contact with Earth across geological timescales strains credulity to the point of collapse. Unless, of course, the protocol is enforced, unless the galaxy is governed by some authority capable of ensuring compliance. But that raises questions far more disturbing than the ones it answers. What kind of power could enforce silence across 1,000,000 light-years of space? What happens to civilizations that violate the protocol? And if such a power exists, why have we not seen evidence of it? The zoo hypothesis does not dissolve the mystery. It relocates it. The second category of explanation involves the nature of communication itself. Perhaps advanced civilizations are not using radio waves. Perhaps radio is a technology that civilizations use only briefly during a narrow window of development, before moving on to communication methods that we cannot yet detect or even conceive of. Just as an ancient Greek had no framework for understanding a radio signal, we may have no framework for understanding whatever communication technology a billion-year-old civilization uses. This is sometimes called the hypothesis of technological transcendence, or the idea that advanced civilizations are simply operating on channels we cannot access. They are not silent. They are broadcasting on frequencies we do not know exist, using modalities we have not discovered, in a language built from physical principles we have not yet derived. We are holding a tin can telephone and wondering why we cannot hear the fiber optic network. This explanation is intellectually honest about our limitations in a way that is genuinely humbling. It acknowledges that our current technology represents a vanishingly small slice of what physics permits, and that beings with billions of years of additional development would have communication capabilities as far beyond our radio. Telescopes, as our radio telescopes, are beyond two sticks, banging together. We might be surrounded by signals of unimaginable sophistication and simply lack the instruments to detect them the way a person deaf to all frequencies above 20 kHz would be unaware of the ultrasonic navigation calls of bats, filling the room around them. But this explanation too has a weakness. Even a civilization communicating primarily through methods we cannot detect would likely also produce detectable side effects of its existence. A civilization that has industrialized its star system would alter the electromagnetic signature of that star in ways that telescopes like the James Webb Space Telescope could potentially detect. A civilization that has built megastructures would block and re-emit starlight in patterns that would appear anomalous to our astronomers. A civilization that has colonized multiple star systems would have left physical traces in those systems, altered planetary compositions, unusual isotopic ratios, structures that do not fit natural formation models that our instruments should to be able to identify, even if we cannot intercept their communication. The absence of these signatures is not explained by the transcendence hypothesis. You can argue that their communications are invisible to us. You cannot as easily argue that their physical presence across star systems is also invisible. If a sufficiently advanced civilization is out there, it should have left fingerprints on the galaxy that we cannot miss, regardless of what communication technology it uses. And yet, the fingerprints are absent. The galaxy looks in every direction we have examined, exactly as it would look if no one had ever been here. Stars follow the distributions predicted by stellar formation models. Planetary systems show no signs of engineering. No megastructures, no Dyson spheres, no evidence of matter organized on scales beyond what gravity and chemistry alone can produce. The universe looks disturbingly like a place where intelligence has not yet had time to leave its mark, and that conclusion fits the data almost too well. This brings us to the third and most haunting category of explanations. The category that does not assume the civilizations are hiding or communicating on channels we cannot detect or respectfully observing us from a distance. The category that asks a different question entirely. Not where are they, but what happened to them. This is the category of solutions centered on the concept of the Great Filter. The Great Filter was first articulated in its modern form by economist and futurist Robin Hanson in a 1998 paper whose title was itself a statement of existential weight. The Great Filter, are we almost past it? The core idea, this: if the universe should contain many advanced civilizations and yet we observe none, then somewhere along the path from lifeless matter to galaxy-spanning civilization, there must be a step or a series of steps so extraordinarily improbable or so lethally difficult that almost no lineage ever gets through it. A filter, a barrier, something that stops the overwhelming majority of potentially intelligent life from ever reaching the stage where it becomes visible across interstellar distances. The filter does not have to be a single dramatic event. It could be a sequence of improbable steps, each one reducing the probability of success by an enormous factor, so that the cumulative product is a probability so small that in a galaxy of hundreds of billions of stars, only a handful of lineages, perhaps only one, have ever made it through. The filter is whatever explains the silence, whatever turns a universe that should be full of voices into one that returns only static. The Great Filter has a structure that forces a choice with no comfortable option. Either the filter is behind us or it is ahead of us. And the implications of each possibility could not be more different. If the filter is behind us, then we have already passed through the most improbable step. Something in our past, in the 4.6 billion year history of Earth and the 3.8 billion year history of life on this planet, was so extraordinarily unlikely that it happened here but almost nowhere else in the galaxy. We are, on this view, the survivors of an almost impossibly improbable sequence of events, the beneficiaries of a roll of cosmic dice that came up in our favor against odds so enormous they dwarf any number a human intuition can hold. The candidate steps for a past filter are numerous. The origin of life itself, the transition from simple chemistry to self-replicating molecules, is not understood even on Earth. We do not know how the first cell came to be. We do not know whether the conditions that produced it were common or vanishingly rare. If the emergence of life requires a specific combination of chemistry, energy, and environmental stability that occurs only once in a billion planetary histories, then life itself is the filter, and we are here because we won a lottery of cosmic proportions. But life, even complex life, is not the end of the story. The transition from simple single-celled prokaryotic organisms, cells without a nucleus, to complex eukaryotic cells, cells with a nucleus and internal organelles, took roughly 2 billion years on Earth and appears to have happened exactly once in the history of this planet. All complex life on Earth. Every plant, every animal, every fungus, every organism with more than one cell type descends from a single ancestral eukaryotic cell that arose approximately 2 billion years ago. In 2 billion years of prokaryotic life in a biosphere, teeming with microbial diversity, this transition happened once, one time, in a lineage that contains every complex organism that has ever lived. If the eukaryotic transition is the filter, then simple microbial life may be common in the universe, but complex life, the kind that eventually produces nervous systems and brains and the capacity for intelligence, may be extraordinarily rare. Not because the universe is hostile to life, but because the specific cellular architecture required for complexity is so difficult to achieve that it occurs almost nowhere. Then there is the transition to intelligence itself. Nervous systems appeared hundreds of millions of years ago on Earth. Complex brains appeared tens of millions of years ago. Language, symbolic thought, and the capacity to accumulate knowledge across generations, the specific cognitive toolkit that allows technology to develop, appeared perhaps 2,000,000 years ago in one lineage of primate. In the entire history of complex animal life on Earth, spanning hundreds of millions of years and millions of species, only one developed the cognitive architecture necessary for science and technology. One. Us. If intelligence is that rare, even on a planet where complex life flourished for hundreds of millions of years, then the galaxy may contain countless worlds, teeming with animals, with ecosystems of remarkable complexity and diversity where nothing ever develops the specific neural architecture that asks questions about the stars, where life remains perpetually brilliant in its diversity and perpetually silent in its sky. If any one of these steps is the great filter, the news for humanity is paradoxically good. We have passed through the most dangerous part of the journey. Whatever killed the others, whatever stopped the vast majority of planetary lineages from producing technological civilizations, we have survived it. We are here. We are capable. The silence of the universe is the silence of a vast graveyard in which we are not buried. We are the unlikely survivors, the rare exception, the ones who made it through. But there is another possibility, a possibility that transforms the same silence into something entirely different, something that is not comforting in the slightest, something that once understood changes the way you look at the night sky forever. The filter may not be behind us, it may be ahead. If the filter is ahead of us, then the silence of the universe is not evidence that we have already passed the most dangerous step. It is evidence that almost every civilization that has ever reached our level of development has subsequently been destroyed or destroyed itself before becoming visible across interstellar distances. The silence is not a graveyard of lineages that never reached intelligence. It is a graveyard of civilizations that reached exactly where we are now and then vanished. The candidates for a future filter are, if anything, more numerous and more immediate than the candidates for a past one. Nuclear war, engineered pathogens, climate collapse, artificial intelligence that optimizes for goals incompatible with human survival, resource depletion. Any civilization that develops the power to alter its planetary environment also develops the power to destroy it. The same technology that allows a species to build radio telescopes and probe the structure of the atom also allows it to split that atom in ways that render its home planet uninhabitable. Perhaps every civilization that reaches our level of technological sophistication hits a wall. Not a physical wall, not a law of physics, but a civilizational wall. A threshold at which the power available to individuals or factions within the civilization exceeds the wisdom required to use it safely. A point at which the gap between what a civilization can do and what it should do becomes fatal, where the weapons become too powerful and the judgment too unreliable and the time too short. If this is the filter, then our own century, this century, right now, may be the most dangerous period in the history of our species. Not because of any single threat in isolation, but because of the convergence of multiple technologies, each one capable of civilizational damage, developing simultaneously faster than the institutions designed to govern them can adapt. And if every civilization hits this wall and most of them fail to get through it, then the silence of the universe is a warning. A statistical echo of 1,000 extinctions. A pattern so consistent that it qualifies as a law of nature. The silence would be telling us that the universe has run this experiment many times, that intelligence is not rare at all, that it emerges, repeatedly develops technology, reaches a threshold of power, and then stops. Not because something external destroys it, but because something internal does. Because the same cognitive architecture that allows a species to understand the universe also allows it to rationalize its own destruction. Because the drive that produces science also produces weapons. Because the curiosity that builds telescopes also builds bombs. And we are running the experiment right now. This is what the silence sounds like when you let yourself hear it fully. Not the comfortable silence of a universe where others exist, but are simply too far away. Not the neutral silence of a universe where communication has not yet occurred. The silence of a universe where the filter is real and recent and may be approaching. There is a thought experiment that physicists and philosophers sometimes use to sharpen this realization. Imagine that tomorrow morning, humanity receives a confirmed signal from an extraterrestrial civilization. Not an ambiguous anomaly, not a pattern that might be natural, but an unambiguous structured information-bearing signal from a world 50 light-years away. The greatest discovery in human history. Proof that we are not alone. Proof that intelligence exists elsewhere in the universe. Now imagine that embedded in that signal is enough information for us to determine the approximate technological level of the civilization that sent it. And we determine that they are roughly at our stage of development. They have radio telescopes, they have spacecraft, they have physics and chemistry and biology. They are, as far as we can tell, a civilization in approximately our situation, broadcasting a signal into the dark and hoping someone hears. How do you feel? Elated, perhaps? Amazed? Moved? The loneliness of the cosmos dissolved in a single transmission. But now consider what it means statistically. If a civilization at our level of development exists 50 light-years away, and another one exists 200 light-years away, and another one 1,000 light-years away, then intelligence at our level is not rare. It occurs at a frequency consistent with many civilizations arising in the galaxy over geological time, which means that many civilizations have arisen before us, which means that many have already passed through our current stage of development, which means that the filter, whatever it is, has not yet claimed them, or it has, and we simply cannot see the ruins from here. And if the filter is ahead, and most civilizations fail to pass it, then finding a civilization at our level is not good news. It is a death sentence written in probability. It means the filter exists and is ahead of us. It means we are not special. It means we are on the same trajectory as everyone else, and everyone else did not make it. Carl Sagan put it differently but arrived at the same conclusion. He wrote that the absence of extraterrestrial signals was potentially evidence of civilizations being common but long lives being rare. That the universe might be full of civilizations that briefly blaze with radio emissions and then went silent, not because they stopped transmitting, but because they stopped existing. This is what the Great Filter means in its most honest form. The silence of the universe is either the best possible news or the worst possible news, and we do not yet know which. The best news is that we are extraordinarily rare, that the filter is behind us, that in a galaxy of hundreds of billions of stars, we are among only a handful of civilizations that have ever reached our current stage. The worst news is that we are not special at all, that intelligence is common, that the filter is ahead, and that the silence is the sound of what comes next. There is no comfortable middle ground. Either we are a miracle or we are a statistic. And sitting in this uncertainty, listening to the silence with our radio telescopes and our equations, we have exactly one piece of information that no equation can fully process. We are still here. The filter, if it is ahead, has not reached us yet. We are still transmitting, still listening, still asking the question that Enrico Fermi asked over a lunch table in New Mexico 3/4 of a century ago. Where is everybody? The silence has not answered, but it keeps speaking, and the longer it speaks, the harder it becomes to pretend that it is saying nothing at all. There is a moment that planetary scientists and astrobiologists have imagined in careful, precise detail. It has been described in scientific papers, debated at conferences, discussed in the offices of NASA and the European Space Agency. It has not happened yet, but the technology to make it happen either exists or is within reach. And when it happens, if it happens, it will be the most significant moment in the history of human civilization. More significant than the moon landing, more significant than the discovery of the heliocentric solar system, more significant than any war, any revolution, any technological breakthrough in the entire recorded history of our species. A rover on the surface of Mars or a probe descending through the ice shell of Europa into the ocean beneath returns a sample. The sample is analyzed, and in the analysis, there is something that should not be there by any purely geological or chemical process. A cell, a membrane, a self-replicating molecule, a structure so improbable, so specifically organized, so unmistakably biological, that the scientists examining the data go quiet in a way that has nothing to do with professional composure and everything to do with the sudden weight of what they are looking at. Life. Not intelligent life, not a civilization, a microbe, a bacterium, or something functionally equivalent to one. A single-celled organism clinging to the underside of a rock or suspended in a pocket of liquid water beneath kilometers of ice. Invisible to the naked eye. Unremarkable by almost any measure. The kind of organism that covers every surface of your kitchen counter and lives in the soil of your garden and has been present on Earth for 3.8 billion years without once building a telescope or asking a question. And it would be the worst possible news humanity has ever received. This is not a paradox. It is not dark humor. It is a direct logical consequence of the great filter, and once you understand the reasoning, you cannot unthink it. The discovery of simple life elsewhere in the solar system would not be a triumph. It would be a warning. It would be the universe telling us, in the clearest possible language, that the filter is not behind us, that we have not yet passed the most dangerous step, that whatever is coming for civilizations, it is still ahead. To understand why, you need to hold two ideas simultaneously. The first is that the great filter must exist somewhere because the silence demands it. Something is preventing the emergence of visible galaxy-spanning civilizations. Something is keeping the universe quiet. The second is that the filter's location relative to us, whether it lies in our past or our future, is the single most important unknown in the history of science. It determines whether we are safe or doomed, whether human civilization has a future measured in millions of years or in centuries. If the filter is behind us, it must correspond to some step in the history of life that was extraordinarily improbable. The origin of life, the emergence of the eukaryotic cell, the development of sexual reproduction, the transition from sea to land, the evolution of intelligence, some step that happened on Earth but almost nowhere else that explains why we are here while the rest of the universe is silent. If the filter is behind us, then the history of life on Earth contains the answer. Somewhere in our past is the miracle that makes us exceptional, the improbable event that we survived and almost no one else did. Now consider what the discovery of life on Mars would tell us about that history. Mars is close. It formed from the same solar nebula as Earth. It received the same bombardment of early asteroids and comets, many of which are now known to carry organic molecules, the chemical precursors to biology. If life arose independently on Mars, in addition to arising independently on Earth, then the origin of life is not the filter. It is not the improbable step that almost no one survives. It is something that happens readily given the right conditions on any world with liquid water and the appropriate chemistry. Life is easy, life is common. Life in that case is the rule rather than the exception. And if the origin of life is not the filter, then the filter must lie further along the path, at some later step, at some transition that comes after the emergence of simple life, a transition that simple life undergoes on some worlds but almost never completes. A transition that produces the silence we observe, not by preventing life from arising, but by preventing it from progressing beyond a certain stage. Every candidate for that later filter is more immediately threatening than the last. If the filter is the emergence of complex multicellular life, then the galaxy may be full of microbial worlds that never produced an animal. If the filter is the emergence of intelligence, then complex ecosystems may flourish on countless worlds without ever producing a mind that looks up. If the filter is the survival of technological civilization past its own power to destroy itself, then intelligence may be common and ruins may be everywhere, silent monuments to civilizations that reached our stage and then stopped. Each of these possibilities becomes more probable if we find life elsewhere in the solar system, because each discovery of independent life pushes the origin of life further from the filter, relocating it to a step that comes later, closer to where we are now, closer to our future rather than our past. Mars life would be one discovery. Europa life would be another. Enceladus, the moon of Saturn whose geysers spray water from a subsurface ocean into space, is another candidate. Titan, with its lakes of liquid methane and its complex organic chemistry, is another. If life has arisen multiple times in our own solar system independently from separate origins, then the origin of life is essentially certain to be common throughout the galaxy. And the filter must lie elsewhere. Robin Hanson, who first formalized the great filter argument, put it with devastating precision. The more places we find life, the more we should fear what comes next. The more evidence we accumulate that biology is common, that cells arise readily wherever conditions permit, the more we should worry that the silence is caused not by the rarity of life, but by the rarity of survival. The more we discover that the universe is full of living worlds, the more we should suspect that those worlds are full of dead civilizations. This is the logic that makes the search for extraterrestrial life one of the most psychologically fraught scientific endeavors in human history. Every scientist involved in the search knows at some level what a positive result implies. They are searching for something whose discovery would be simultaneously the greatest triumph and the most sobering warning in the history of our species. They are looking for a microbe that could be a death sentence written in biology. But let us now turn the logic around, because the great filter argument cuts both ways and the other direction is important. If we search Mars and find nothing, if we drill through Europa's ice and find sterile water, if we analyze the plumes of Enceladus and detect no biological signatures, if every corner of the solar system beyond Earth returns the same answer, absence, then the filter may genuinely lie behind us. The origin of life may be extraordinarily rare. The specific chemistry that produced the first self-replicating molecule on Earth may have been so improbable, so contingent on a specific sequence of unlikely events that it has happened only once in the history of the galaxy, or a handful of times, or a number small enough to explain the silence without requiring that civilizations inevitably destroy themselves. If life is rare, we are safe, or at least we have passed the most dangerous hurdle. The universe's silence is not a warning about our future. It is a testament to our improbability. We are here not because we are heading toward a cliff that every civilization falls from, but because we are the outcome of an extraordinarily unlikely series of events that almost never occur. The empty skies above us are not the ruins of 1,000 civilizations. They are the expected result of a universe where life almost never gets started at all. This is the strange beauty of our current ignorance. We do not yet know whether the solar system beyond Earth is sterile or teeming. We have not yet returned samples from Mars. We have not yet penetrated Europa's ocean. We have not yet analyzed the chemistry of Enceladus's plumes with sufficient sensitivity to detect biological molecules. The answer to the most important question in the history of science is sitting in our own solar system within the reach of technology we already possess, waiting to be discovered. And until we find it, we are suspended between two interpretations of reality, so different that they define opposite futures for our species. In one future, the solar system is barren beyond Earth. Life is rare. We are a miracle. The great filter is behind us. The path ahead, though uncertain and full of challenges, is open. The silence of the universe is the silence of an empty stage on which we are among the first performers to appear. Perhaps the first. Perhaps the only ones who will ever stand here and look out at the dark and wonder if someone is watching. In the other future, the solar system is not barren. Mars has life or had it. Europa's ocean teems with organisms adapted to cold and pressure and darkness. Enceladus sprays biological molecules into space with every eruption of its geysers. Life is common. The great filter is ahead. The silence is not empty. It is the silence of civilizations that went quiet one after another throughout the history of the galaxy, each one reaching a threshold of technological power that it could not survive. We are standing at that threshold right now. Consider what the 20th century did to the species that built it. In the span of a single human lifetime, we developed the ability to extinguish ourselves with nuclear weapons. We altered the chemistry of the planet's atmosphere in ways that are already producing measurable consequences that will persist for thousands of years. We engineered pathogens in laboratories. We built artificial intelligence systems whose decision-making processes exceed our ability to fully understand or predict. We did all of this not out of malice, but out of curiosity, out of the same drive to understand and control the world that produced medicine and agriculture and art. The tools and the weapons come from the same source. The same mind that cures disease can engineer it. The same physics that generates clean energy can produce weapons of mass destruction. If this is true of us after only 200 years of technological development, what does it look like after 1,000 years? After 10,000? After 1,000,000? Does the power available to individuals and subgroups within a civilization continue to grow without bound? Does the wisdom required to wield that power scale at the same rate? Or is there a gap, a permanently widening gap between capability and judgment that every civilization must eventually cross and from which most do not return? The Fermi Paradox does not answer this question. It cannot. We have one data point ourselves, and we have not yet finished running our own experiment. But the silence of the universe applies pressure to every answer we might propose. Because if civilizations routinely survive their technological adolescence and go on to colonize the galaxy, there should be evidence of them everywhere. The absence of that evidence suggests that routine survival is not the norm, that some filter, intercepts most civilizations somewhere along the path. And the most uncomfortable possibility, the one that fits the data without requiring extraordinary assumptions, is that the filter is the civilization itself. That intelligence, everywhere it arises, creates the conditions of its own extinction. That the same cognitive flexibility that allows a species to model the universe also allows it to rationalize catastrophic choices. That the same social structures that enable cooperation on small scales fail to scale to civilizational problems. That the same technological acceleration that produces radio telescopes eventually produces something that the civilization cannot survive. There is a concept that the astrobiologist David Grinspoon has written about with unusual clarity. He calls the transition from a young technological civilization to a mature one the cosmic challenge. The question is not whether a civilization can develop technology. Clearly it can. The question is whether it can develop the wisdom to govern that technology before the technology governs it. Whether it can extend its moral circle from the tribe to the species to the biosphere fast enough to prevent the tools it has built from being turned against the systems that sustain it. Grinspoon argues that civilizations that pass this challenge become something qualitatively different from what they were before. They become stable on geological timescales. They develop what he calls long sight, the ability to think and plan across centuries and millennia rather than years and decades. They align their technology with the maintenance of the systems that support them rather than the exploitation of those systems until they collapse. They become, in a word, sustainable in a way that young civilizations almost by definition are not. And civilizations that fail this challenge stop. They stop expanding. They stop communicating. They stop leaving marks on the galaxy. They go quiet in exactly the way that the universe in every direction we look has gone quiet. If this is the filter, it is not a wall that kills from the outside. It is a threshold that civilizations fail to cross from the inside. A developmental crisis that most intelligent species encounter and most do not survive. Not because they are destroyed by something external, not because a supernova sterilizes their world or an asteroid strikes at the wrong moment, but because they destroy themselves, because the gap between what they can do and what they should do becomes eventually fatal. We are a civilization that can split the atom and cannot consistently agree on how to share food. A species that can send probes to the edge of the solar system and cannot reliably prevent the collapse of ecosystems that have sustained life for millions of years. A kind of being that can look up at the night sky and comprehend the structure of the cosmos and look down at its own history and see a consistent pattern of self-inflicted catastrophe. We are, in other words, a civilization that is either approaching the filter or has somehow stumbled through the early stages of it and is still improbably here, still transmitting, still listening, still asking the question. And the answer to that question, whatever it is sitting somewhere in the solar system waiting to be found. In the rust-colored soil of a frozen world, 78 million kilometers away at its closest approach. In the dark water beneath 25 kilometers of ice on a moon of Jupiter. In the plumes of a moon of Saturn that erupts into space with the contents of an ocean that has been liquid for perhaps billions of years. We will find the answer. The technology exists, or is close to existing. The missions are being planned. The samples are being collected. Within decades, perhaps sooner, we will know whether the solar system beyond Earth is biologically empty or biologically rich, whether life is the miracle or the rule. And when we know that we will know something about the filter, we will know with more clarity than we have ever had whether it lies behind us or ahead, whether the silence of the universe is the silence of an empty stage or the silence of a graveyard. One of those answers is wonderful. The other is the most important warning our species has ever received, delivered not by a prophet or a government or an authority of any kind, but by the universe itself in the only language it has ever used with us: silence. On the night of August 15th, 1977, a radio telescope in Delaware, Ohio, was doing what it had been doing every night for 3 years: listening. The telescope was part of Ohio State University's Big Ear Observatory, a structure unlike the elegant dish-shaped instruments most people associate with radio astronomy. Big Ear was a flat reflector, a vast metal plane lying on the ground like a fallen mirror, 103 meters wide and 21 stories tall when measured at its reflective surface, designed to collect radio waves from the sky as the Earth rotated beneath it. It had been scanning the heavens continuously since 1973, part of a systematic survey of the entire sky that its operators hoped would eventually reveal a signal from somewhere beyond the solar system. The telescope did not have a human operator sitting at a console watching the data in real time. It printed its output on paper, long rolls of computer printout, covered in columns of numbers, representing signal intensity at different frequencies. A volunteer researcher named Jerry Eman would review these printouts by hand, scanning the columns for anything that deviated from the background noise of the universe. It was painstaking work. Most of what the telescope heard was nothing, static, the electromagnetic murmur of a cosmos going about its business, without addressing anyone in particular. On August 15th, at precisely 10:16 p.m. Eastern Time, Big Ear heard something different. The signal appeared at a frequency of 1420.456 MHz, extraordinarily close to the emission frequency of neutral hydrogen that Frank Drake had identified 16 years earlier as the most logical channel for interstellar communication. It was narrowband, meaning it was concentrated at a single frequency rather than spread across a range, exactly the signature that distinguishes an artificial transmission from the broadband noise of natural astrophysical sources. Stars emit across broad swaths of the spectrum. A deliberate signal engineered to be recognized would concentrate its energy at a single point. The signal's intensity rose and fell in exactly the pattern that Big Ear's beam would produce as it swept across a fixed point in the sky during the Earth's rotation. A source that was genuinely stationary in the sky, a star, a galaxy. Anything not moving with the Earth would appear to grow stronger as it entered the telescope's beam, reach a peak at the center, and then fade as the beam swept past. The signal that Big Ear recorded on the night of August 15th followed this pattern precisely. It rose, peaked, and fell over the course of 72 seconds, with a curve that matched the telescope's expected response to a fixed point source almost perfectly. The signal was 30 times stronger than the background noise of the sky. 30 times. In radio astronomy, a signal that's strong does not come from nothing. It does not arise from instrument noise or terrestrial interference or any known natural astrophysical process. It appeared to come from a specific direction in the constellation Sagittarius, a region of sky with no known natural radio source capable of producing an emission of this character. When Jerry Eman reviewed the printout days later and saw the column of numbers representing the signal's intensity, he did something that has become one of the most famous gestures in the history of science. He circled the numbers in red ink and wrote a single word in the margin. Wow. The signal is known to this day as the WOW signal. It remains nearly 5 decades later the strongest candidate for an extraterrestrial transmission ever detected. It matched every criterion that SETI researchers had established for what a genuine alien signal should look like. Narrowband, at the hydrogen frequency, following the correct intensity profile for a fixed sky source, stronger than any known natural background, coming from a direction with no identified radio source. It was by every measurable criterion available in 1977 exactly what humanity had been listening for, and then it was gone. Big Ear returned to that region of sky again and again in the weeks and months following the detection. The telescope listened for 50 subsequent observations targeting the same coordinates, hundreds of hours of observation time, straining its instruments toward the same patch of Sagittarius that had produced the extraordinary signal on August 15th. It heard nothing, not a whisper, not a faint recurrence, not a degraded echo of what it had detected. The silence that followed the WOW signal was as complete and absolute as the silence that had preceded it. Other radio telescopes joined the search. The Very Large Array in New Mexico, the Arecibo Observatory in Puerto Rico, then the largest single-dish radio telescope on Earth, more sensitive instruments, longer observation times, better technology. None of them found anything at those coordinates. None of them reproduced the signal. None of them found any trace of what Big Ear had heard on that August night. The WOW signal was heard once for 72 seconds by a telescope that was not looking for it reviewed, days after it occurred by a volunteer researcher who circled it in red ink and has never been explained. Not in 1977, not in 1997, not in 2017, not now. Scientists have proposed natural explanations. A hydrogen cloud in the galaxy emitting at the hydrogen frequency, a comet passing through the field of view outgassing hydrogen in a way that mimicked a narrowband signal. The comet hypothesis was specifically proposed in 2017 by Antonio Paris of St. Petersburg College, who suggested that 2 comets, 266P Christensen and 335P Gibbs, were in the vicinity of the WOW signal's origin point on the night of the detection. The hypothesis generated significant media coverage. It also generated significant scientific skepticism. Other researchers pointed out that comets do not typically produce narrowband radio emissions at the hydrogen frequency with the intensity profile that Big Ear recorded. The comet hypothesis remains contested and has not achieved consensus. The honest scientific answer nearly 50 years after Jerry Eman wrote his single word in the margin of a computer printout is that we do not know what produced the WOW signal. We cannot explain it naturally with any mechanism that has achieved broad scientific acceptance. We cannot explain it artificially without invoking an extraterrestrial transmitter of extraordinary power aimed deliberately or accidentally in the direction of our solar system. We heard something once for 72 seconds, and it has never spoken again. This is what the search for extraterrestrial intelligence actually feels like from the inside, not the triumphant moment of contact that science fiction has rehearsed in 1,000 stories, not the gradual accumulation of evidence that leads to a press conference in a changed world, a signal in the night, a red circle in a margin, decades of silence that follow like a held breath that never releases. The WOW signal is the most dramatic example of this pattern, but it is not the only one. The history of SETI is littered with moments when the silence was broken by something anomalous, something that demanded attention, something that raised the pulse of everyone who examined it, followed by the same conclusion: no confirmation, no recurrence, no explanation. In 1997, astronomers using the Parkes radio telescope in Australia detected a series of intense radio bursts that seemed to come from beyond the galaxy. These fast radio bursts, as they came to be called, are now understood to be a genuine astrophysical phenomenon produced by exotic natural sources, most likely magnetars, the ultra-dense remnants of collapsed stars with magnetic fields so intense they strain the limits of physics. But for years their origin was unknown, and their strangeness, their brevity, their extraordinary intensity placed them on the long list of phenomena that briefly occupied the space between natural explanation and deliberate signal. In 2015, a star approximately 1400 light-years away in the constellation Cygnus began behaving in a way that no star in the history of astronomical observation had ever behaved before. The star catalogued as KIC 8462852, but known to the public as Tabby's star, after the astronomer Tabetha Boyajian, who led the team studying it, was dimming, not in the regular, predictable way that stars dim when a planet passes in front of them, the transiting signal that Kepler used to detect thousands of exoplanets. Tabby's star was dimming irregularly by different amounts, at different times, sometimes by as much as 22% of its total brightness, a dimming so extreme that no planet, no matter how large, could produce it. A planet the size of Jupiter dims its star by roughly 1% when it transits. Something was blocking 22% of the light from Tabby's star. Something large, something irregular, something that did not fit any natural model that astronomers could confidently apply. The excitement that followed was immediate and enormous. Astronomer Jason Wright of Penn State University raised the possibility carefully and with appropriate scientific caution that the dimming pattern was consistent with what a Dyson swarm might look like from a distance. A Dyson swarm is a variant of Freeman Dyson's original concept, a collection of structures, solar panels, habitats, collectors built by a civilization to capture the energy of its star. Not a single solid shell, which would be structurally implausible, but a cloud of independent objects, orbiting the star in complex patterns that could produce irregular asymmetric dimming as they passed between the star and a distant observer. Tabby's star was for a period of months the most discussed object in astronomy, not because the alien megastructure hypothesis was considered likely by most scientists, but because it was considered possible in a way that most anomalies are not. The data was real, the dimming was real, the natural explanations were insufficient, and the alternative, a structure built by intelligence at stellar scales, could not be immediately ruled out. Subsequent observation and analysis gradually assembled a more mundane picture. The dimming appears to be caused by dust clouds of fine particles orbiting the star in irregular configurations, possibly the remnants of a disrupted comet family or a collisional event involving smaller bodies in the system. The dust hypothesis fits the wavelength-dependent behavior of the dimming in a way that a solid structure would not. Tabby's star is almost certainly not surrounded by alien megastructures. Almost certainly. The qualifier remains as it always does with these cases. The data is consistent with dust. The data does not absolutely exclude other explanations. The universe in its complexity occasionally produces phenomena that sit at the edge of our explanatory reach, and the honest scientist must acknowledge that edge, even while being reasonably confident about which side of it the truth lies. In April of 2019, astronomers using the Parkes telescope in Australia detected a radio signal appearing to come from the direction of Proxima Centauri, the nearest star to our Sun, located approximately 4.2 light-years away. The signal was at a frequency of 982.002 MHz, a narrowband emission that did not correspond to any known natural radio source. It appeared in the data collected in April and May of 2019, but was not noticed until late 2020, when a team from Breakthrough Listen, the most well-funded SETI initiative in history, was reviewing archived observations. The signal designated BLC-1 for Breakthrough Listen Candidate 1 generated intense interest within the scientific community, and when it leaked to the press, an extraordinary wave of public attention. Proxima Centauri is the nearest star. It has a planet Proxima b in its habitable zone, a signal appearing to come from the direction of the nearest star, with a known, potentially habitable planet at a narrowband frequency, with no obvious natural explanation, is precisely the scenario that SETI researchers had spent 6 decades hoping to encounter. The excitement lasted several months. Then the analysis deepened. The signal appeared only when the telescope was pointed at Proxima Centauri. It did not appear when the telescope pointed away. This is exactly the behavior expected of a genuine extraterrestrial signal. But it is also consistent with radio frequency interference from a terrestrial source that happens to align with the telescope's direction of observation. Human technology produces radio emissions at a vast range of frequencies. Aircraft, satellites, military equipment, communication systems, scientific instruments all contribute to a radio environment so crowded that distinguishing a genuine extraterrestrial signal from terrestrial contamination is one of the central technical challenges of radio astronomy. By early 2021, the Breakthrough Listen team had concluded that BLC-1 was most likely caused by radio frequency interference of terrestrial or near-Earth origin. The signal's frequency drifted in a way that suggested a moving source, possibly an aircraft or satellite, rather than a fixed point in the sky. The candidate was retired. Proxima Centauri returned to silence. This is the rhythm of the search. Signal, attention, analysis, silence. Again and again, across 6 decades, the universe offers something that briefly resembles contact, and then resolves into noise, into natural phenomena, into terrestrial contamination, into the electromagnetic clutter of a technological civilization listening to itself and occasionally mistaking its own reflections for a voice from outside. And yet the search continues, not out of stubbornness, not out of wishful thinking, but because the alternative stopping means accepting the silence as final, means deciding that we have listened enough that the absence of a confirmed signal is definitive that the universe has given its answer, and the answer is that we are alone. And that conclusion, if it is wrong, has consequences as significant as any in the history of science. Because if someone is out there and we stop listening, we may miss the signal that changes everything. Breakthrough Listen, funded by a $100 million commitment from Russian-Israeli entrepreneur Yuri Milner, announced in 2015, represents the most ambitious SETI program in history. It uses the world's most powerful radio telescopes, including the Green Bank Telescope in West Virginia and the Parkes Telescope in Australia, to observe targets including the 1 million nearest stars, the center of the Milky Way, the 100 nearest galaxies. It processes data at rates that dwarf anything the early SETI pioneers could have imagined, using machine learning algorithms trained to identify anomalies in the electromagnetic noise of the sky. It has published its data openly, making it available to any researcher who wants to analyze it. It has found nothing. Not a confirmed signal, not an anomaly that survived rigorous scrutiny, not a pattern in any dataset that requires an extraterrestrial explanation. 6 decades of searching from Drake's primitive receiver at Green Bank in 1960 to the petabytes of data processed by Breakthrough. Listen today, and the result is the same: silence. The most sophisticated instruments ever built by the most technically advanced civilization in the known history of the galaxy. Listening across a vast range of frequencies and directions and times, and hearing nothing that unambiguously says someone else is there. But here is what that silence does not mean. It does not mean we have heard everything. It does not mean we have listened everywhere at every frequency in every modality, with sufficient sensitivity to detect every possible kind of transmission. The electromagnetic spectrum is vast. The galaxy is enormous. Our instruments, however, powerful by the standards of 1960, remain primitive by the standards of what physics permits. We have searched a tiny fraction of the possibility space. We have listened to a small number of stars at a small number of frequencies for a short period of time, The absence of a confirmed signal is real and significant, but it is not yet exhaustive. The history of SETI is not a history of failure. It is a history of a search that has not yet found what it is looking for. These are different things. A search that has not succeeded is not the same as a search that has proven its target does not exist. The WOW signal reminds us of this every time we return to it. Something happened on the night of August 15th, 1977. Something produced 72 seconds of data that has never been explained. The universe briefly said something or appeared to, and then returned to its customary silence before anyone could ask it to repeat itself. Jerry Eman, the man who found the signal, spent years trying to explain it naturally. He was a scientist, not a dreamer, and he applied scientific rigor to the question of what Big Ear had recorded. He could not explain it. In a 2010 paper reviewing the evidence, he concluded that the signal's origin remains unknown and that the possibility of an extraterrestrial origin cannot be ruled out. Cannot be ruled out. In the careful, qualified language of science, these 4 words carry enormous weight. They mean that after decades of analysis, after every natural explanation has been examined and found wanting, the data is still consistent with something that science does not yet know how to account for. That a single night in Ohio, in 1977, produced 72 seconds of data that remains in the strictest scientific sense unexplained. The WOW signal did not answer Fermi's question, but it did something almost as important. It demonstrated that the universe is capable of producing or appearing to produce exactly the kind of signal that SETI researchers had predicted a genuine extraterrestrial transmission would look like. It proved that the search was not chasing a phantom, that the criteria established by Drake and his colleagues for what contact would look like were physically realizable, that a signal matching those criteria could exist and could be detected by instruments like Big Ear. It also demonstrated with painful clarity the fragility of discovery in a universe this large. A signal that lasts 72 seconds and is never repeated cannot be confirmed. It cannot be analyzed with sufficient depth. It cannot be shown to other telescopes in real time. It cannot be answered. It simply exists in the data, a permanent anomaly, a 7-2-second interruption in 6 decades of silence, a moment when the universe seemed to speak and then thought better of it, or never spoke at all. That possibility remains open, as it always must in science. The WOW signal may have a natural explanation not yet identified. The universe is under no obligation to produce phenomena that fit our categories. It has surprised us before and will surprise us again. The history of astronomy is a history of phenomena that seemed impossible until they were explained: pulsars mistaken initially for artificial signals, fast radio bursts whose origin baffled astronomers for years, cosmic rays whose energies seemed to violate physical constraints until their sources were identified. The universe is strange. Its strangeness does not always point toward intelligence. More often, it points toward natural processes operating at scales and in regimes that our intuitions built for a world of moderate temperatures and moderate energies are poorly equipped to imagine. But sometimes the strangeness lingers. Sometimes it resists every natural explanation offered to it and sits in the data like a question mark that no one has yet been able to erase. The WOW signal is that kind of strangeness. It has been sitting in the data for nearly 50 years. It has been examined by some of the finest radio astronomers in the world, and it is still there, still circled in red ink, still in the margin of a computer printout from 1977, wearing the word that a careful scientist wrote when he did not know what else to say. Wow. That word is the most honest summary of the search for extraterrestrial intelligence that has ever been written. Not a confirmation, not a refutation, a response to something that exceeded expectation. A single syllable that contains within it all the hope and all the uncertainty and all the strangeness of a species that has been listening to the universe for 60 years and heard in all that time one thing it cannot explain, and then silence again, always eventually silence. There is a version of the Fermi Paradox that requires no filter, no catastrophe, no civilization that destroyed itself, no protocol of silence maintained across geological time by every advanced species simultaneously. a version that does not require the universe to be dangerous or hostile, or governed by some invisible law that terminates intelligence before it can spread. A version in which the silence is not a warning and not a mystery, and not a sign of anything ominous waiting in our future. In this version, the silence is simply the expected result of a universe in which worlds like ours are extraordinarily, almost impossibly rare. This is the rare Earth hypothesis first articulated in systematic form by paleontologist Peter Ward and astronomer Joe Kirschvink, building on work by Donald Brownlee in their 2000 book of the same name. The core argument is this: the conditions that allowed complex life to arise on Earth are not merely favorable. They are the product of an improbable convergence of factors, each one individually uncommon, that together constitute a set of circumstances so specific, so precisely calibrated, so dependent on the simultaneous satisfaction of dozens of independent requirements that their occurrence on any other world in the galaxy may be extraordinarily rare, perhaps unique. The rare Earth hypothesis does not argue that life is impossible elsewhere. It argues that complex life, the kind that produces animals and nervous systems and intelligence, requires something that simple microbial life does not. It requires a planet that has not merely crossed the threshold of habitability, but has maintained it continuously across billions of years of geological and astronomical change, and maintaining habitability across billions of years, in a universe as violent and variable as ours, requires a combination of factors so specific that the galaxy may contain billions of worlds with microbial life and almost none with anything more complex. To understand why, begin with location. Not the location of the planet within its solar system, though, that matters enormously, but the location of the solar system within the galaxy itself. The Milky Way is not a uniform structure. It is a barred spiral galaxy with regions of dramatically different character. Near the center, the galactic core stellar density is extraordinarily high. Stars are packed close together. The gravitational interactions between them are frequent and violent. Supernovae, the explosive deaths of massive stars, occur far more often near the core than in the outer regions. Each supernova releases a burst of gamma radiation powerful enough to sterilize any planet within hundreds of light years. The core is also home to Sagittarius A times the supermassive black hole at the center of the galaxy, whose periodic activity generates radiation environments hostile to the complex chemistry that life requires. Near the outer edge of the galaxy, stellar density drops to levels so low that the heavy elements produced by previous generations of dying stars, elements like carbon, oxygen, nitrogen, iron, the building blocks of biology and planetary geology, become scarce. Planets in the outer galaxy may simply lack the raw materials for complex chemistry. They may be too metal poor, too chemically impoverished to build the molecular machinery that life requires. Between these extremes lies what astronomers call the galactic habitable zone, a ring-shaped region of the Milky Way centered roughly where our solar system sits, far enough from the core to avoid its radiation and gravitational violence, close enough to the inner galaxy to benefit from the heavy element enrichment produced by billions of years of stellar evolution. The galactic habitable zone is not a sharp boundary, but a gradient, and our sun sits near its center. This is not a coincidence in the way that a lottery win is a coincidence. It is a selection effect. We could not have evolved in the core or in the outer galaxy. The conditions there are incompatible with the development of complex life. But the fact that we occupy a favorable position in the galaxy does not mean that favorable positions are common. The galactic habitable zone contains perhaps 10 to 20% of the Milky Way's stars. The rest sit in regions where the development of complex life faces additional barriers that may prove insurmountable. Now consider the Sun itself. Our star is a G-type main sequence star, a yellow dwarf unremarkable by stellar standards. It is neither the largest nor the smallest class of star, neither the hottest nor the coolest, neither the most nor the least luminous. But its unremarkability conceals a specific set of properties that turn out to matter enormously for the development of complex life. The Sun is unusually stable. Its luminosity has increased by roughly 30% over the 4.6 billion year history of the solar system, a gradual brightening that has been offset by geological and biological feedbacks on Earth's climate, but which has never varied wildly or rapidly enough to sterilize the planet. It does not produce the intense stellar flares that are common in smaller, cooler red dwarf stars, the most abundant stellar type in the galaxy. Red dwarf flares can strip atmospheres and bathe planetary surfaces in ultraviolet radiation at levels lethal to complex life. Our sun flares occasionally, but at levels that Earth's magnetic field and atmosphere handle without difficulty. The sun is also a single star. Roughly half of the stars in the Milky Way exist in binary or multiple systems, two or more stars orbiting each other. Binary systems can produce planetary orbits that are chaotic, gravitationally unstable, or subject to dramatic variations in stellar radiation as the planet moves relative to two suns rather than one. Stable circular planetary orbits of the kind that maintain consistent climates across billions of years are harder to achieve in binary systems. Single stars like our Sun are more conducive to the long-term orbital stability that complex life requires. Now move inward from the Sun to Earth itself, and the specificity becomes even more striking. Earth orbits the Sun at a distance of approximately 1 astronomical unit, placing it squarely within the habitable zone where liquid water can exist on the surface. This is the Goldilocks condition, not too hot and not too cold, that everyone learns about in school. But the habitable zone is not the whole story. Many planets orbit within their star's habitable zone. What matters is not merely whether a planet can have liquid water, but whether it maintains liquid water across billions of years, despite the constant perturbations of geology, orbital mechanics, and stellar evolution. Earth has managed this because of a set of stabilizing mechanisms that are on reflection not at all guaranteed. The carbon-silicate cycle, a geological feedback loop in which carbon dioxide is removed from the atmosphere by weathering of silicate rocks sequestered in carbonate minerals, subducted into the mantle by plate tectonics, and returned to the atmosphere by volcanic outgassing, acts as a planetary thermostat. When Earth warms, increased rainfall accelerates weathering and removes carbon dioxide from the atmosphere, cooling the planet. When Earth cools, reduced rainfall slows, weathering carbon dioxide accumulates, and the greenhouse effect warms things back up. This feedback has operated for billions of years, keeping Earth's surface temperature within the range compatible with liquid water, despite the gradual brightening of the Sun and despite massive perturbations from impacts and volcanic events. The carbon-silicate cycle requires plate tectonics. Not all rocky planets have plate tectonics. Venus, our nearest neighbor, is almost exactly the same size as Earth, formed from the same solar nebula, and sits at a distance from the Sun only slightly closer than ours. Venus has no plate tectonics. Its interior heat escapes not through the steady and continuous recycling of a mobile crust, but through periodic catastrophic resurfacing events that may release enormous quantities of carbon dioxide into the atmosphere all at once. Venus today has a surface temperature of approximately 465 degrees Celsius, hot enough to melt lead under a crushing atmosphere of carbon dioxide and sulfuric acid clouds. Venus is Earth's twin in size and origin, and a completely different kind of hell in every other respect. The difference between Earth and Venus may come down in part to whether plate tectonics got started, and we do not yet fully understand why it did on one world and not the other. Now consider the Moon. Our Moon is enormous relative to Earth. The Moon's diameter is roughly 27% of Earth's, making it by far the largest moon relative to its parent planet in the solar system, with the exception of Pluto and its moon Charon, which most astronomers now classify as a binary dwarf planet system. Our Moon is so large relative to Earth that the two bodies are sometimes called a double planet system. The Moon is the product of an improbable catastrophe. Approximately 4.5 billion years ago, a Mars-sized body that planetary scientists have named Theia collided with the proto-Earth in a glancing blow of extraordinary violence. The collision melted both bodies, ejected an enormous quantity of material into orbit, and that material coalesced into the Moon. It was a specific kind of impact, at a specific angle, at a specific velocity, involving a specific size of impactor. Slightly different conditions, and the result might have been a debris ring that never consolidated, or a smaller moon that did not provide sufficient gravitational influence, or a direct hit that destroyed both bodies entirely. The moon that resulted from this improbable collision has had profound consequences for the development of life on Earth. The moon's gravitational influence stabilizes Earth's axial tilt. Earth's axis is currently tilted at approximately 23.5 degrees relative to its orbital plane, and this tilt varies only slightly over long timescales due to the moon's stabilizing effect. This stability is critical for climate regularity. A planet whose axial tilt varies chaotically, as Mars's does in the absence of a large stabilizing moon, would experience dramatic rapid climate swings as its poles alternately face toward and away from the Sun at different angles over geological time. Such swings might prevent the long-term climatic stability that allowed complex life to develop on Earth. The moon also drives Earth's tides. Tidal mixing of the oceans distributes nutrients and regulates ocean chemistry in ways that have been important for marine biology throughout the history of life. Some researchers have proposed that the tidal zones created by the moon's gravitational influence, shallow coastal areas that alternately flood and drain, created the environmental conditions that drove the evolution of the first land-dwelling organisms. The moon may have been not merely a stabilizing influence, but an active participant in the evolutionary history of complex life. Now consider Jupiter, the solar system's largest planet, a gas giant containing more mass than all the other planets combined, orbits the Sun at a distance of 5.2 astronomical units beyond the asteroid belt and well outside the region where terrestrial planets formed. Jupiter's enormous gravitational influence shapes the entire architecture of the inner solar system in ways that have been critical for the development of life on Earth. Jupiter acts as a gravitational vacuum cleaner, capturing or ejecting comets and asteroids that would otherwise rain down on the inner solar system with far greater frequency. Early in the solar system's history, Jupiter's gravity sculpted the distribution of material in the asteroid belt, preventing it from coalescing into a planet and reducing the density of impactors available to strike the inner worlds. Without Jupiter, the impact rate on Earth over its 4.6 billion-year history might have been significantly higher, potentially resetting biological progress repeatedly and preventing the accumulation of complexity that eventually produced multicellular life. This is sometimes called the Jupiter shield hypothesis, and it has become somewhat more nuanced in recent years. Newer dynamical models suggest that Jupiter's influence is not purely protective, that under certain configurations it can also scatter comets into the inner solar system rather than deflecting them outward. But the basic insight remains. The presence of a large gas giant in the outer solar system, positioned where Jupiter sits, appears to reduce the frequency of catastrophic impacts on inner solar system planets. And catastrophic impacts at sufficient frequency are incompatible with the development of complex life. Bring all of these factors together. A star in the galactic habitable zone, a single stable yellow dwarf star that does not flare violently, a rocky planet in the habitable zone with plate tectonics and a carbon silicate thermostat, a large moon that stabilizes axial tilt, a gas giant in the outer solar system that reduces impact frequency. Each factor individually is not extraordinarily rare. Some fraction of stars occupy favorable galactic positions. Some fraction of those have suitable spectral types. Some fraction of those have rocky planets in habitable zones. But the probability of all of these conditions being simultaneously satisfied on a single world begins when you multiply the fractions together to approach numbers that strain the imagination. Ward and Brownlee estimated using conservative assumptions that planets with the full suite of conditions favorable to complex life might be extraordinarily rare, possibly numbering in the thousands or less in a galaxy of hundreds of billions of stars. More recent analyses have produced a wide range of estimates, some more optimistic, some more pessimistic, but the underlying logic of the rare Earth argument has not been decisively refuted. The specific combination of factors that made Earth suitable for complex life over billions of years is not obviously common. It may be extraordinarily uncommon. And there is one more factor that Ward and Brownlee emphasized, one that is perhaps the most sobering of all: time. The development of complex multicellular life on Earth took approximately 3.5 billion years from the first appearance of simple cells. Intelligence took another several 100 million years beyond that. The total time from the formation of Earth to the emergence of a technological civilization is 4.6 billion years. This is not an arbitrary number. It is a constraint imposed by biology and evolution. Complex life does not arise quickly. It accumulates slowly through billions of generations of selection, through hundreds of millions of years of ecological interaction, through geological processes that operate on timescales that make human history look like a rounding beaver. Error. A planet that satisfies all the physical requirements for complex life but is too young has not yet had time to produce it. A planet that satisfied all the requirements but was located near a star that died before 4.6 billion years had passed was never going to produce intelligence, regardless of how favorable its initial conditions were. The Sun is roughly halfway through its main sequence lifespan, with approximately another 5 billion years before it begins to expand into a red giant. This places us in an extraordinarily fortunate temporal position as well as a spatial one. If the rare Earth hypothesis is correct, the Fermi Paradox dissolves. There is no paradox. The universe is not teeming with civilizations that should be visible and are not. The universe contains scattered across its 2 trillion galaxies an enormous number of worlds with microbial life and an extraordinarily small number with complex life. The number with intelligent technological civilizations may be in the dozens or the single digits, or precisely one. The silence is not a mystery requiring a filter, or a catastrophe, or a protocol of non-interference. It is simply the expected result of a universe in which the conditions for complex life are met almost nowhere. We are not survivors of a filter. We are not racing toward a cliff. We are simply alone. Not because something killed the others, but because the others never existed. Not in the numbers that the naive application of the Drake equation suggests. Not in the numbers that would fill the galaxy with signals and megastructures and evidence of engineering on cosmic scales. The rare Earth hypothesis offers a kind of peace that the other explanations do not. It tells us that the silence is not a warning and not a verdict. It is the natural state of a universe in which we are, if not unique then, among the most improbable outcomes that 13.8 billion years of cosmic evolution has produced. It tells us that Earth is not an ordinary world among billions of similar ones, but something closer to a miracle, a world that got everything right one factor at a time, across 4.6 billion years of geological and biological history, and produced at the end of that improbable sequence something that could look up and understand what had happened. But the peace that the rare Earth hypothesis offers is not without its own weight. Because if we are rare, if complex life is uncommon, and technological intelligence is rarer still, then what happens here matters in a way that extends far beyond our own survival. If we are among only a handful of civilizations in the galaxy capable of asking questions about the universe and receiving answers, then the loss of this civilization would not merely be a tragedy for human beings. It would be a loss for the cosmos itself, a subtraction from whatever small number of minds the universe has managed to produce in 13.8 billion years of effort. The rare Earth hypothesis does not make our future less precarious. In some ways, it makes it more so, because it suggests that what we have here on this specific world at this specific moment in the history of the solar system is not replaceable. There is no backup civilization waiting to inherit the questions we leave unanswered. There is no other species on another world that will, if we fail, carry forward the project of understanding the universe and our place in it. There may be no one else. That possibility that we are genuinely alone, not as a failure of contact, but as a consequence of our rarity, changes the silence into something different from what Fermi's paradox initially suggested. The silence is not the sound of dead civilizations. It is not the sound of civilizations hiding or civilizations communicating on channels we cannot access. It is simply the sound of a universe in which minds are rare, in which the conditions for intelligence are met almost nowhere, in which the fact that we exist at all is so improbable that no human language has yet developed adequate words for it. We are here, against odds that dwarf any number intuition can hold, on a world that got everything right across 4.6 billion years of change and catastrophe and geological violence. around a star that sits in the right part of a galaxy that formed at the right time, with a moon that stabilizes our seasons and a planet that shields us from the worst of the cosmic bombardment, with plate tectonics that regulate our climate and an atmosphere that filters the radiation that would otherwise strip the chemistry of life from our surface. We are here, and the silence that surrounds us may not be the silence of absence. It may be the silence of rarity, the silence of a universe that has produced in nearly 14 billion years, only a small number of places where something looks up and wonders. And we are one of them. That is either the loneliest thought in the history of science, or the most humbling depending on what you choose to do with it. We have come a long way from a lunch table in New Mexico. We started with a question so simple it could be spoken in 4 words. Where is everybody? And we have followed that question through the mathematics of stellar formation and the architecture of the Drake equation, through the history of a search that has spanned 6 decades and produced one circled anomaly on a paper printout, and a silence that stretches in every direction we have pointed our instruments. We have sat with the great filter and felt its weight, the way it forces a choice between 2 interpretations of reality so different that they define opposite meanings for human existence. We have stood at the edge of the rare Earth hypothesis and looked out at a universe in which the conditions for complex life are met almost nowhere, in which the fact that we exist at all is the most improbable outcome that 13.8 billion years of cosmic evolution has produced. And now we return to the question, not to answer it, we cannot answer it, not yet, but to hear it differently than we did at the beginning. To understand that the question has changed in the asking that the silence it points toward is not the same silence. We started with that. 4 words spoken over a lunch table in 1950 have grown in the decades since into something that contains the entire history of life and the entire uncertainty of its future. Where is everybody? The honest answer in 2026 is that we do not know. We have not found them. We have not confirmed their absence. We have searched a small fraction of the possibility space with instruments that are powerful by human standards and primitive by cosmic ones. We have listened at frequencies that seemed logical to us in directions that seemed promising for periods of time that feel long in human terms and are negligible in astronomical ones. We have found one anomaly that has never been explained, 172 second signal from a summer night in Ohio that sits in the data like a question mark no one has managed to erase, and we have found silence everywhere else. But silence, as we have learned, is not simple. It is not a single thing. It is a collection of possibilities, each one carrying a different weight, each one pointing toward a different future for the species that is doing the listening. The silence might mean that they are too far away, that the galaxy is full of voices and we simply have not heard them yet because the distances involved are so vast that signals traveling at the speed of light take longer to cross them than our civilization has existed. That somewhere right now a signal is crossing the void between us and a civilization that broadcast it thousands of years ago, and it has not yet reached us. And when it does, the silence will end in an instant, and the universe will reveal itself as the populated, communicating ancient structure that the equations suggest it should be. The silence might mean that they are communicating in ways we cannot detect. That radio waves are a technology of civilizational adolescence, used briefly and then abandoned for something more sophisticated that we have not yet discovered, leaving behind a universe full of conversations we are not equipped to overhear. That the cosmic silence we experience is not the silence of an empty universe, but the silence of a receiver that is tuned to the wrong frequency. A child pressing its ear to a wall trying to hear a symphony being performed in a medium the child does not know exists. The silence might mean that they are watching, that we inhabit a protected region of the cosmos observed by civilizations advanced enough to have established protocols of non-interference, waiting for us to reach some threshold of development before making contact. That the silence is not absence but restraint, not emptiness but patience, not loneliness, but a kind of respect that we have not yet done anything to earn. The silence might mean that they are gone, that the filter is ahead, that intelligence arises readily in the universe, and just as readily destroys itself that the galaxy is littered with the ruins of civilizations that reached our stage of development and then encountered a threshold they could not cross, a gap between capability and wisdom that proved fatal, a technology that outpaced the judgment required to govern it, that the silence is the silence of 1,000 extinctions, each one playing out on a different world in a different century, each one leaving behind a planet slowly healing from whatever the civilization did to it, each one returning to the silence that preceded intelligence and will outlast it. The silence might mean that we are alone, not as a consequence of the filter or the distance or the communication mismatch, but as a simple fact of cosmic demographics, that the conditions for complex life are met so rarely that the improbable sequence of factors that produced Earth is so specific and so contingent that in a galaxy of 400 billion stars, only a handful of worlds have ever produced anything more complex than a microbe, that the silence is the natural acoustic of a universe in which minds are precious and vanishingly rare, in which the emergence of a species capable of asking questions about the cosmos is an event so improbable that it may have happened only once. Each of these possibilities is real. Each of them fits the data we have. None of them can be ruled out by anything we currently know. And this uncertainty, this irreducible not knowing that sits at the heart of the Fermi Paradox, is not a failure of science. It is science doing exactly what it is supposed to do, holding open the space between hypothesis and confirmation, refusing to collapse possibilities into certainties before the evidence demands it, maintaining, in the face of the most enormous question our species has ever asked, the intellectual honesty to say we do not yet know. But not knowing is not the same as having nothing to say, because the silence, regardless of its cause, has already done something to us. It has already changed the way we think about the planet we live on and the moment we occupy in the history of life. It has already altered the meaning of the night sky above our heads, transforming it from a backdrop into a statement, from decoration into data, from the familiar ceiling of human experience into the most significant unresolved question in the history of science. Look up on a clear night away from the light pollution of cities, and you see approximately 5,000 stars with the naked eye, each one a sun, each one we now know with near certainty surrounded by planets, each one a possible address for something that thinks and wonders and asks. 5,000 points of light, and behind each one billions of years of stellar history, and around each one worlds we will not visit in our lifetimes or in our children's lifetimes or in the lifetimes of our children's children. And behind those 5,000 stars, invisible to unaided human eyes but real, present part of the same universe, 200 billion more in this galaxy alone. And beyond this galaxy, 2 trillion others, each one a structure of comparable scale and complexity, each one containing its own billions of stars and its own trillions of planets and its own billions of years of history. In all of that, we have heard nothing. In all of that, the only unambiguous voice belongs to us. The only confirmed mind belongs to this species on this world, orbiting this star in this galaxy, at this moment in the 13.8 billion year history of the cosmos. Either we are extraordinarily alone, or we are extraordinarily early, or we are extraordinarily fortunate to have survived long enough to ask the question. Perhaps all three, perhaps none. The silence does not yet permit certainty, but it permits something else, something that may be more important than certainty in the long run. It permits wonder. Not the shallow wonder of novelty, not the brief amazement that flares and fades when a new image from the James Webb Space Telescope crosses your screen and is replaced by the next thing your attention is drawn to. The deep structural wonder that comes from sitting with a question long enough to feel its full weight. The kind of wonder that changes the way you move through the world, because it has changed the way you understand the world you are moving through. The silence of the universe is the most profound context in which any human life has ever been lived. Every person who has ever existed, every joy and grief and ambition and failure, every civilization that rose and fell, every war and every peace, every discovery and every forgetting, has occurred against the backdrop of this silence. A silence so large that no human scale can hold it. A silence that has been present since the first stars ignited and will persist in all probability, long after the last human voice has spoken its last word. And yet here we are, shouting into it, with radio telescopes and mathematical equations and spacecraft named after scientists who died before they could see what the instruments found. With a 7.2-second recording from 1977 that we have been trying to explain ever since. With rovers on Mars and probes approaching the ice of Europa, and observatories pointed at every corner of the observable universe, all of them asking the same question in different ways. Are we alone? We do not know. We may not know in our lifetimes. We may not know in our grandchildren's lifetimes. The answer may require technology we have not yet built, experiments we have not yet designed, observations we have not yet made. It may require visiting other worlds with instruments sensitive enough to detect the chemistry of life in a rock sample or an ocean current or the plume of a geyser erupting from beneath kilometers of ice. But we are looking. That is perhaps the most remarkable fact of all. A species that has existed for roughly 3,000,000 years, that built its first cities less than 1,000,000 years ago, that split the atom less than a century ago, that launched its first satellite into orbit less than 70 years ago, that placed its first footstep on another world in 1969, is now pointing instruments at stars thousands of light years away and asking whether anyone there is doing the same thing. A species so young, by cosmic standards, that its entire existence occupies less than a single frame of the universe's history, has nonetheless developed the capability to address the most fundamental question that a conscious being can ask about it. Situation. Are we alone in a universe this large and this old? The question itself is evidence, not of intelligence in the abstract, not of cognition in the general sense, but of a specific and extraordinary kind of mind, one that can perceive the universe at scales from the subatomic to the cosmological, one that can hold in a single thought both the smallness of its own existence and the vastness of the structure it inhabits, one that can feel the weight of its own improbability and respond not with paralysis but with curiosity, one that can sit in the silence and hear in it not defeat but invitation. Enrico Fermi asked his question in 1950 at a lunch table in the tone of a man who had noticed that the numbers did not add up. He did not live to see the wow signal. He did not live to see the Kepler mission confirm that planets are everywhere. He did not live to see the James Webb Space Telescope image, the atmospheres of worlds orbiting other stars searching for the chemical signatures of biology. He did not live to see any of the answers that the decades after his death produced to the question he asked over lunch. But the question survived him. It grew. It attracted the attention of the finest scientific minds of the following 3 generations. It generated research programs and radio telescopes and space missions and mathematical frameworks and philosophical arguments that have collectively produced the most sustained and rigorous scientific investigation of a single question in the history of our species. And it has not yet been answered. That is not failure. That is the condition of being at the frontier. The frontier is the place where knowledge ends and the unknown begins, where the questions are larger than the answers, where the silence is not evidence of defeat, but evidence of how far there still is to go. Every generation that has ever lived at the frontier of human knowledge has experienced this condition. The astronomers who first pointed telescopes at the sky did not find all the answers. They found better questions. The physicists who split the atom did not reach the end of matter. They found layers of structure that had not previously been imagined. The biologists who sequenced the genome did not solve the mystery of life. They discovered a language so complex that we are still learning to read it. The silence of the universe is our generation's version of this condition, the most important question we have ever asked, held open by the limits of what we can currently hear and see and measure, waiting for the instruments that will sharpen our senses, waiting for the missions that will reach the places where the answer might be written in rock or ice or ocean chemistry, waiting for the moment which may come in a decade or a century, or never, when the silence breaks, or does not break, because that too is a possible answer. The silence may be the final answer. We may search for 1,000 years with instruments of unimaginable sophistication and find at the end of all that searching that the universe contains no other voice, that we have been alone all along in every sense that matters, that the silence was not a puzzle to be solved, but a fact to be accepted, the most significant and most humbling fact in the history of science. If that is the answer, then the silence becomes something different from what it seemed at the beginning of this journey. It becomes not a problem, but a responsibility. If we are alone, then everything that consciousness has ever produced, every thought and every question and every attempt to understand the universe that has ever occurred anywhere in the history of the cosmos, has occurred here, on this world, in these minds. In the 3,000,000 years of Homo sapiens, and the millions of years of pre-human cognition that preceded it, and everything that consciousness will ever produce if we are alone, depends on what happens next. On whether this civilization, this one, the only one, manages to cross whatever threshold lies ahead, manages to close the gap between what it can do and what it should do, manages to extend its existence long enough to become something that the universe has never seen before, something that builds and maintains rather than builds and destroys, something that earns by its continued existence the right to be called a long-term feature of the cosmos, rather than a brief, bright flash in an otherwise dark night. The silence is asking us something. It has been asking since Fermi posed his question over lunch, and the question it is asking is not merely, where is everybody? It is asking whether we will still be here, whether we will still be listening 1,000 years from now, whether the silence will eventually be broken by us, by a signal carrying the mathematics and the biology and the music of this world outward into the galaxy, announcing that at least one mind has survived its own adolescence and is ready to be part of whatever conversation the universe is or is not having. Step outside tonight. Let your eyes adjust to the dark. Find a patch of sky away from the cities and the light that we pour into the night like water from a broken dam. Look up. Let the stars resolve from a blur into points of light, each one a sun, each one surrounded by worlds. You will never visit each one a possible address for a question that has no confirmed answer. Listen, not with your ears. The universe does not carry its signals through air. Listen in the way that Fermi listened, with the part of the mind that notices when the numbers do not add up, when the expected and the observed diverge in a way that demands explanation, when the silence is so large and so complete that it begins against all reason to feel like something being said. The universe is 13.8 billion years old. It contains more stars than the human mind can hold. It has been running the experiment of chemistry and gravity and nuclear physics for longer than any timescale human intuition can genuinely grasp. And in all of that, in all of those years and all of those stars and all of that unimaginable expanse of space and time, the only confirmed voice is ours. One voice, in a silence that stretches farther than light, has traveled since the beginning of time. One candle burning in a darkness so vast that the darkness is not metaphor but mathematics. One mind, or rather 7 billion of them, packed onto a small rocky world orbiting an ordinary star in the outer reaches of one galaxy among 2 trillion, asking the oldest question and receiving in return the oldest answer. Silence. But we are still asking. And as long as we are asking, the silence is not final. It is only waiting. For better instruments, for braver missions, for the patience to keep listening long after the listening has returned nothing, for the wisdom to understand that a question this large deserves a search that matches it in scale and in duration and in the quality of attention brought to it. The universe is not obligated to be populated. It is not obligated to be friendly or legible or organized in ways that make our existence feel less improbable. It owes us nothing, and yet it has produced us. It has generated in at least one place the conditions necessary for matter to organize itself into structures capable of asking questions about the structure of matter. It has produced at least one mind capable of looking up at the stars and wondering whether the stars are looking back. That is extraordinary. Whatever the silence means, whatever explanation eventually resolves the paradox that Fermi identified over lunch in 1950, this fact remains. We are here. We are conscious. We are asking. In a universe that had no obligation to produce any of those things, it produced all 3. The silence surrounds us on every side. It has surrounded us since before we existed. It will surround us long after we are gone, whether we last another century or another billion years. It is the default state of the cosmos, the background against which everything that has ever happened has happened. But tonight on this world, in this moment, something is listening to it. Something small and improbable and briefly alive is pointing its instruments at the sky and waiting for the silence to speak. We are that something, and we have not stopped listening yet.